We're going to do an example and to determine the pressure of water at each of the three states defined by a temperature of 100 degrees Celsius and specific volumes of, at state 1, we have a specific volume of 2.434 cubic meters per kilogram, state 2, 1 cubic meter per kilogram, and state 3, a specific volume of 1.0423 times 10 to the negative 3 meters cubed kilograms. So although they're asking us to find pressure, we're also going to eventually sketch the temperature specific volume diagram, a pressure specific volume diagram, as well as we'll talk about how we would, what we call fixing the state. We could find our other state properties, and the properties we are looking at that define a state are temperature, pressure, specific volume, specific internal energy, specific enthalpy, and specific entropy. So this process could be used to find all of these state variables. So what we're given here is temperature and volume, specific volume in SI units. Again, Celsius and meters cubed, we know that we have SI units. And so we're going to use this handout to find, to gather some data. So we can see here, when we look at our table, this is, we go down this column until we find the one that fits what we have. So we have temperature and specific volume, and so we're going to look up temperature on table A2 because we have SI units, and we're going to find VF and VG. These are the saturated liquid and saturated vapor values for specific volume. So we're going to do that, and then we're going to come back and see where we land on these charts. So using table A2 in SI units, we're going to look up a temperature of 100 degrees Celsius. So this is table A2, and we're going to look at 100 degrees Celsius, and we find this row of values that pertains to 100 degrees Celsius. So for a T of 100 degrees Celsius, we have T equals 100 degrees Celsius. We have VF equal to, it's right here, 1.0435 times 10 to the negative third. That's a 3, 10 to the negative third meters cubed kilogram. And just taking a moment here to see, this says here, so first of all, this is specific volume, and the units are meters cubed kilograms. Then here is saturated liquid, so VF here, that's saturated liquid, and this says saturated liquid times 10 to the third, and I wrote 10 to the negative third. But what this, the way this table is set up is it's saying that all of the values in this column here, all of these values are multiplied by 10 to the third. So if I have these values and I'm multiplying them by 10 to the third, then I get this value. So in what that means is my value is actually that 1.0435 times 10 to the negative third. And so then that's the value we use. And we can see here that we have a value of 1.673 for our saturated vapor, so VG, and this isn't multiplied by anything, so this one is just the value that is on the table, 1.673 meters cubed kilograms. And we can also take this value here, this is our saturated pressure. So PSAT here, PSAT is the second column. This first column here is temperature on table A2. On table A2, temperature is in the first column, and then we have pressure in the second column, and that pressure is the saturated pressure. So PSAT is in this second column here. Right here, all of these values are the saturated pressure values associated at a given temperature. So PSAT for our 100 degrees Celsius is 1.014 bar. And that, if we're in the dome, then that would be our pressure. So these are our VF and our VG. And again, here we have state 1, state 2, and state 3 specific volumes that we are going to see where they lie. So first of all, well, let's just compare 1, 2, and 3 there with our VF and VG and see where they lie with that. So V1 is greater than, so V1 is greater than VG. This one is greater than this one. And V2 lies between, so VF is less than, V2 is less than VG. This value is between this value and this value. And then the third one here we have V3. So V3 here is less than VF. So if we go back up to our table up here, we can see that for state 1, so state 1 here, where we're greater than VG, we can see that we have a superheated vapor. So this is vapor, and that we're going to use table A4 to find our values for that one. And then for the B here, we have, we're between the two. So we know this is a two-phase liquid vapor, and that we need an additional property. We're going to have to find quality, and we're going to use our calculations, our quality calculation to find this, and we're going to use table A2. And for the third one here, we can see that if we're less than, if V3 is less than VF, then this is a compressed liquid. And so we have a liquid, and here we're going to try to use table A5, and if that doesn't work, then we'll find an approximate value using the table A2. So that's what we're going to do right now, and we're going to find all of the pressure values that are associated with this. We already know the pressure value that would be associated with this second one. If we're in this dome range here, inside there, then our pressure is going to equal PSAT. We know that because in the dome there, the temperature and the pressure are the same. So we know this is 1.014 bar. But we can find quality, and we could find our other state properties by looking, using the table. So let's continue on here. So let's look at just state 1 first, and then we get state 2 here. So state 1, again, we have a temperature of 100 degrees, a temperature of 100 degrees Celsius, and a specific volume of this, and we know that we're greater than VG, and so we have a superheated vapor, and we're going to use table A4. That's what we discovered above there. So here's table A4, and I'm going to use this to find my value. So I look through table A4, and I find where I have a temperature of 100 degrees Celsius and a specific volume given of 2.434. And so we find it on our chart, luckily. If it wasn't here, we would maybe have to interpolate to find it, but we do have it here. And so we can see that our pressure is 0.70 bar, and for that pressure, our TSAT is 89.95 degrees Celsius, and Then our other values are here as well. Our internal energy is here, and this is units of kilojoules per kilogram. And we have our enthalpy, specific enthalpy. We can just pull all of these right off of this table. This is 2680.0 kilojoules per kilogram, and so on. So these are the state properties. We can just look them up. We know that this is a vapor. We know that these are the values associated with that. We can continue on here for state 2. We have, in the case of state 2, we have 100 degrees Celsius, and we have a specific volume of 1 cubic meter per kilogram. And we again see that it falls between these values. We know that then it is two-phase liquid vapor mixture. We're in the vapor dome, and we need to find quality and use quality to find the properties on table A2. In this case, we know that P equals PSAT, which is 1.014 bars. So here is table A2, just the part of A2 that we need to get our values from. And so we can see here that VF, we found VF is right here, multiplied by 10 to the negative 3, and here is VG. So using those values and our given specific volume, we can find quality using this formula. It comes from this formula which we were given in our book, and we just have rearranged it to be a ratio here. So quality is going to equal the specific volume I'm given, 1.0 meters cubed kilogram, minus VF, which is 1.0435 times 10 to the negative 3 meters cubed kilogram. And then that is divided by our VG, which in this case is 1.673 minus VF, which is 1.0435 times 10 to the negative third meters cubed kilogram. And then I just have to do this calculation, and I find that my quality is 0.5975. And there's no units on this. The units all here cancel. Oops, I lost my units here. This would be 1.673 meters cubed kilograms. So anyway, our units all cancel, and this is just a ratio of where we are in the dome, how far across we are. We're a little bit more than halfway through the dome. And then we can use this value and these equations here. So we can use our UF and UG values here, and then given our quality, X, that would be the 0.5975, and then we can determine our internal energy. And likewise, we can use our HF here, and let's see here, sorry about that, HF and HG, we can use those here and here, or we can use this additional value here, and this one is here. HFG is simply HG minus HF. And so just, we use it a lot, so we just put an extra place on your table so you don't even have to do that subtraction. You can just use this value. And that you can use that to determine H here. So we can use this value. So HF plus quality times the term HFG is going to give me the specific enthalpy at this state, 100 degrees Celsius, and a specific volume of 1 meters cubed per kilogram. And then the same thing can be done with entropy. So that is how we find our properties at state 2. State 3, again, you might recall that we had a temperature of 100 degrees Celsius, a specific volume of 1.0423 times 10 to the negative third cubic meters per kilogram, and that lies right between lies less than VF, and so we know that we are in a compressed liquid, and we're going to use table A5. If it turns out that we can't use table A5, we look at table A5 and our values just aren't on there, then we're going to use table A2 and approximate it. But here on table A5, we do in fact have the 100 degrees Celsius and our exact value. It's nice of them to give us an exact value here to find on our table. It doesn't always work that way. A lot of times we have to interpolate, but we can see here are our values. Again, this one is times 10 to the third, so our value is times 10 to the negative third, and that's correct here. So this would be our exact value that we're given for state 3. And so then we can just see that our state properties for internal energy for state 3 here, U3 would be 418.24 kilojoules per kilogram, and so on, enthalpy, and so on. But here is what we're really looking for. So we can see at the top of this table, P equals 25 bar, and then Tsat, the saturated temperature at 25 bar would be 223.99 degrees Celsius. We could also look on table A3 and look up 25 bar and see what the saturated temperature, this would be the temperature that's in the second column.